Hello, welcome back. Here we're conquering the topic of the introduction to the derivative in calculus. Calculus is based upon the derivative. Everything that follows comes from what we learn in this very first introductory lesson on derivatives. So what we're going to do is I'll give you a practical example of what derivatives are. Spoiler alert, you already know what a derivative is from everyday life, so we'll talk about that. Then we'll talk about the limit definition of the derivative. We'll still be sketching some pictures to make sure we understand that, and then we'll solve problem at the end and problems in the next lesson. Okay, in order to understand conceptually what a derivative is, we're going to talk about everyday life. Position of a particle, or position of a car, position of an airplane, right? Velocity of an airplane, acceleration of an airplane. Position, velocity, acceleration, they're all interrelated. You already know what these things mean. It turns out that these various terms that we have words for, they are what we call derivatives in calculus, right? So we have derivative. When we say the word derivative, before we get started with the drawing, I want you to replace in your mind, anytime you read the word derivative or see the word derivative, I want you to replace it with rate of change. How does something change with respect to something else? Because in everyday life, in actual science and engineering and mathematics, things are changing all the time. The air temperature is changing as a function of time. The velocity of the particles in the room are changing as a function of their position in the room. So if we want to know how things change as time goes on or as a function of distance, we have to study rates of change. In calculus, the word that we use for that is called the derivative. So replace it in your mind with the phrase rate of change. That's very, very important. All right, so let's take a practical example of something you know about, and that's the position of a particle, but it could be the position of anything. Position of the airplane, position of, this position of the marker as it flies around the room, and so on. And over time, this marker is moving around the room. We're going to plot the position of some particle as a function of time. Now, in real life, we have 3 dimensions of space, x, y, z, and we also have time, which is like another dimension. But in the beginning, when we talk about how things change, we're going to restrict the motion to be along only one direction, only one dimension of x. So yeah, there's x, y, z, but forget about y and z. We're only talking about motion forwards and backwards along a straight line, in other words. So this axis over here will be the time axis, and that'll be in seconds. And over here, we're going to have the position of some particle as a function of time, and the unit of this is going to be in meters. So I'll put meters right down here. All right, now to make it interesting, I don't want to talk about super simple motion. So let's talk about something that we might actually see. What if you had some sort of situation? I'm not even going to put tick marks, but there are tick marks: 1 second, 2 second, 3 second, 4 seconds, and it's however many meters the thing goes off into the future. But to keep it clean, let's keep the axes clear here, and let's take a look at some sort of parabolic motion like this. This is the shape of a freehand parabola, half of a parabola anyway. And so let's say then that the position as a function of time was equal to t squared. So what this is telling me is if I have a graph like this, this is the distance away I am from the origin as a function of time. So at 0 seconds, 0 squared is 0, so I'm at a position of 0. But at 1 second in the future, 1 squared is 1, I'm 1 meter away from the starting point. In fact, if I hold like a meter stick up here, I can slide this back here and I can say this is in centimeters, right? And so basically this is plotting how far away I'm getting from the origin as a function of time. And because as time goes on, 1 second, 2 second, 3 second, 4 seconds, you can see that I start pulling away very, very rapidly, or I'm covering more distance in the same amount of time. So I'm sort of accelerating. I'm kind of like speeding up as time goes on. And you can see that because when the graph starts over here, I'm not moving very far at all in distance away. But over here, the 1 second interval over here, I'm traveling a very far distance here. So if it helps you, you can put these little tick marks: 1 second, 2 second, 3 second, 4 seconds, 1 meter, 2 meter, 3 meter, 4 meter. And so in this 1 second interval of time, I don't move very far in meters, but in this 1 second interval of time, I'm moving pretty far. So as time goes on, I'm covering more distance. So that's why the shape of this thing, it looks curved, because as time marches on, I'm covering a greater quantity of distance per second is what's really this graph is telling us. All right. So we could use, right now we're doing position as a function of time, but I want you to know that as we discuss these ideas, these ideas apply to any graph, f of x, where x could be any variable. I'll give examples of that as we get a little bit later in the lesson. I'm motivating it as a function of time as time ticks on. But just so you know, it applies to a function of any variable: position, distance, displacement, time, even a function of temperature. Lots of things are a function of temperature. As temperature changes, things may change, and the weather and things like that. So in this case, it's a function of time. Now, what is going to happen if we want to figure out how the position of this particle changes as a function of time? What we've explicitly said is that here in the beginning, it doesn't appear that the motion is really changing all that fast, because here's a 1 second interval of time and I don't change very much. But here's a 1 second of time where I am changing a lot more. So it appears that I'm speeding up as I go along. So what we're going to talk about is the term derivative. Derivative means rate of change. So if I want to take and show you what the derivative of the position function of any object is, then it's going to be the rate of change of the position. Now think in your mind, what do you know of that is commonly called the rate of change of position? Now you don't say it like that, but that's what we call the velocity of a particle. Think about the units of position. It's meters, right? But then we have the velocity of a particle. We call it meters per second. Look at the units, meters per second. It's a comparison between how far something moves in a fixed or a given amount of time. So it's a combination of units, distance and time. So if we want to figure out the rate of change of this thing, we know that it's changing very rapidly here, very gingerly here, not very much. And we know it's changing very, very fast over here. Now, in calculus, we talk about the rate of change all the time. And we're going to learn that the rate of change, called the derivative, is the slope of the line tangent to a curve. Right? Now we have learned in algebra that we have the slope of a line. Here is a medium slope of a line. Here is a very steep slope of a line. When it's horizontal, the slope of a line is 0. But if I ask you, what is the slope of this thing? Well, you're not going to know what to say because it's not straight line. So if I ask you what is the slope of this thing like right here, what would you tell me? Well, it's curving, so you probably wouldn't know. So in calculus, what we say is the slope of a line, or the rate of change of something, is the slope of the line that is tangent, which just means barely touching at one point the curve. Now I have a lumpy freehand curve, so it's not perfect, but you get the idea. As if I want to know the slope of the curve here, or the derivative, the rate of change, I draw a line tangent to the curve down here, and you can see that this ruler is almost exactly flat here, so the derivative, the rate of change, is very close to 0, or is exactly equal to 0 down here. And as we go over here, the slope of the line tangent gets steeper and steeper and steeper. When it's over here, the slope of the line tangent, or the rate of change, is much, much steeper. So what I'm trying to get you to understand is that by looking at a position curve, if you want to figure out its derivative, which means its rate of change, then you have to look at each moment in time and see how steep the line that's tangent to the curve is. We're going to learn all about this in calculus, but if we want to sketch what that looks like, I'm going to give you the punchline, and I'm not going to prove it to you here. We're going to prove it later, and we're going to talk about it a whole lot more later. But in this next curve down, directly down below from here, again, this is going to be the time axis in seconds, but instead of plotting the position, I'm going to plot something else called the derivative. And so it's related to the original curve, but instead of, so we call it P of t, but we put a prime here, a little, like a little mark, a little apostrophe right there. And the way that you say this is P prime of t. Or you would say it in words, the derivative of P of t. And remember, the word derivative means rate of change. So if I tell you find the derivative of the position function, what you mean in your mind is, or what you say, is what is the rate of change of the position function? Well, the rate of change is always changing because it's a curve function. So what we have to do is say, well, what is the slope, or what is the rate of change of the curve down here, which is going to be very, very low. The slope of the line tangent to the curve here is going to be a little bit more. The slope of the line tangent to the curve here is going to be higher, and the slope of the line tangent over here is going to be even higher. So if I'm plotting the derivative, I'm literally plotting the rate of change of the line tangent to this original curve at any given point. And since it's 0 here, that means the slope, which is the rate of change, P of t, is going to be 0, right? And way over here, the slope is a maximum. So I'm going to put a dot right here. And everywhere in the middle, it turns out that the slope here, it turns out that if this actually is a parabola with that equation, then this becomes a straight line. Now, I can't draw a freehand straight line, so I apologize for that. So you just got to use your imagination and pretend that this is a straight line. Okay? Make sure you understand what this graph is telling you. We're saying that the derivative of the original function, right, is the slope of the line tangent to this original curve at any point. The slope here is 0, so the derivative is 0. The slope here, the slope of the line tangent, is a little bit higher than 0, so this graph is a little higher. The slope here is a little higher, so the graph here is a little higher. The slope here is a little bit higher still, and so it's higher and higher still. Now, we're not going to prove this right now because we haven't gotten into it yet, but I'm going to tell you later that p prime of t, whenever we calculate it, if the original curve was t squared, it's going to be equal to 2 times t. Now, this is the equation of a line. Remember, the equation of a line is mx plus b, right? Where b is the y-intercept, and so if you graph this, the y-intercept is 0, so it hits down here, and the slope of this thing, of this curve, is 2 here. Now, you're not supposed to know at this point how I know that it's this. I'm going to teach you how to find derivatives later. But for any function that you could come up with, literally any function you could write down of any variable, I will teach you how to take a derivative. But what that derivative represents is how fast is the original function changing with respect to time or whatever variable you're studying at any point in the original function. In other words, what is the rate of change? And what this derivative tells me is that the rate of change is 0 of the original function here. The rate of change here is bigger than 0, but less than the maximum value. If I had a real graph, I'd read the value off, and that would be the rate of change. It would be the medium value because it's sloping up here. And the rate of change here is higher than any of these other places. So when you look at a curve and you're asked to sketch the derivative, what you're doing is sketching the slope of the line tangent to the original curve at any point in time. All right? Now, let's move along, and we're going to draw a third curve down below, and then I'm going to write some notation down here that we're going to use pretty much every day for the rest of your calculus life, right? I promise that if you stick with me, calculus will seem very, very simple, and you'll wonder why, you ever had any problems with it, if you ever did. All right, so if this is time in seconds, what if I want to take the derivative of this curve, right? So if this one was called p prime of t, the derivative of p, well, I can actually take the derivative of this thing again, and that would be called p double prime of t. And what it means is I start with p, I take one derivative and get this, and I start with this and I take another derivative called the second derivative and I get this. So the double prime means I've taken 2 derivatives on the original function and I end up here. The first derivative is this one. To get to the next one, I have to take the derivative of this. So let me ask you, what is the derivative of this curve? Remember, anytime you see the word derivative, you replace it with what is the rate of change of the function, which means what is the slope of the line tangent to the curve. Well, in this curve, the slope is always changing. But here, this is just a straight line. So if I want to take the derivative of this, I just have to figure out what the slope of this line is, because it's never changing like it was before. So what is the slope of this thing? Well, look at this. I'm giving you the answer ahead of time that this line, equation of this line, is 2 times t. So what is the slope of this line? It's just the number 2. Right? And the slope of the line here is 2, and the slope of the line here is 2, and the slope of the line here is 2, and the slope of the line here is 2, and the slope is never changing. So if this is 1 and this is 2, then the slope of this line, which is the derivative of that second function right there, is a straight, a horizontal line like this. Right? So p prime of t. So basically what you're doing is to go from this curve to this curve, you're looking at the slope of the line tangent to the curve at any point. And when you go from this curve to this curve, you're also looking at the slope. But in this case, the slope is constant, so you just get a constant graph here. So the derivative graph is telling you how much the original function is changing with respect to time or space or whatever you're studying at any point on the graph. And this line tells us that the curve above is not changing its slope value at all. Its slope is always 2. Now, we started this by talking about position, velocity, and acceleration. So here is the position. Again, this is like so many meters away from the origin over some function of time. And we said that we take the derivative and we get the velocity. So this thing is called the velocity of the particle, right? And we took the derivative again, and we said, okay, we get another graph down here. So if the derivative of position is velocity, if you take the derivative again and take a look at how this thing is changing, the velocity is changing, what do you think this graph is going to be called there? That one's going to be called acceleration. So you have experience with these words already, okay? The derivative of position is velocity, meters per second. But the derivative of velocity is what we call acceleration. It represents how much your velocity is changing over time. And we call, in units, that is meters per second squared. So the first unit is meters up here. So I'm going to put the unit here is, I'll put it in brackets, meters. That's the unit here. But then when we get down here, the unit is meters per second because we're looking at how does this position change over time. So the units are meters per second. And then when we take the derivative down here, the unit is meters per second squared because we're taking a look at how the velocity changes over time. So it's like meters per second. And that's why you get this squared thing on the bottom, meters per second squared, because it's meters per second. How much are you speeding up every second? How much are you slowing down every second? When you're at a red light and you floor it and you get thrown back, your velocity is changing quickly. So you have an acceleration. If you hit the brakes and you slow down, you get thrown forward, your velocity is changing. That's what we call an acceleration, or a negative acceleration, or a deceleration, okay? So these in words is what a derivative is. The rate of change of this curve is always changing. And so the slope is different of the line tangent at all times, which is how we arrive at this graph. But this graph is already a straight line, and so its slope is never changing, and that's why this one, the acceleration graph, is flat. So if this were representing a real particle, it means I would have a constant acceleration. It would be like if I had a rocket ship in space and I turn the thruster on and I'm constantly accelerating at 2 meters per second squared, then my velocity would always be increasing. And because of that, my position curve would be pulling away very rapidly. In other words, it would start slow and then it would go faster, like that. All right, so that in words is what a derivative is. Now, we have to go into notation a little bit more. We already used the prime notation, so over here on the side, we're going to do that in a little more detail, and then I'm going to introduce the definition of the derivative in a more mathematical way. All right, so over here we have the particle's position as a function of time. That's kind of what we started with. All right, now down below, when I changed to the blue color, we took the derivative, and we basically said that the derivative was called p prime of t. But now I'm going to tell you that that's the same thing as what we call the velocity of the particle. So if I tell you or give you a graph of the velocity of the particle, you know now that that means that's the derivative of the position function as a function of time. So p prime of t is exactly the same thing as the velocity as a function of time, or the velocity function, right? And another way to write this, instead of p prime of t, another way that we can write it is we can say that this is dp dt, like this. So this is where, right here, when I write something like this down, this is where a lot of students turn off immediately. They're like, well, I don't understand anymore. What does that mean? Okay, remember back from algebra, right? You learned a long time ago what a slope of a line was, right? Rise over run. It's literally just a division of the rise, how far a graph goes up and how far it goes over. But guess what? Rise over run is a fraction, right? There's something on the top and there's something on the bottom. And you just divide the numbers and you get the slope. And the bigger the slope is, the steeper the graph is, right? That's what it is. The lower the slope, the shallower the graph is. And if it's a slope of 0, then it's a horizontal line. There is no slope at all, right? That's what it is. Rise over run, though, is a fraction. So when I write something in calculus like dp dt, that means that this is the change in the position of the particle divided by the change of some elapsed time period. This is rise over run, in other words. So when you, in calculus, see dp or dt or dm or dx or dy or dz or d anything, the little d just means teeny tiny amount. That's what it means. That's what I want you to think about. if I asked you to tell me what the slope of the line tangent to this curve here, what would you do? You would zoom into this curved surface as far as you could until it almost looked flat, and then you would take the tiny, tiny, tiny rise and a tiny, tiny, tiny run to calculate the slope of the line tangent. So that's a tiny, tiny, tiny rise. dp means how far does the function go up. dt is how far does it go over, rise over run. But when you see dp over dt, it means a tiny, tiny rise in the function at some point, a tiny, tiny elapsed time, divide the two, I get the slope of the original curve. So this is how we write derivatives. We can say it as p prime of t, that means the derivative of the position function. We can also write it as dp dt, which means the change in the position as a function of time. That's exactly what I've been saying in words. Now another way that you can write it, which is not as often, but you can do it this way, you could say p with a little dot on the top. So all of these ways are different ways to say the derivative of the position function. You could just call it the velocity function v of t if you want, or you could say p prime of t, or you could say dp dt, or you could say p with a dot on the top, and the dot means derivative. All right, there's many ways to write derivatives down. It's all notation, but they all mean exactly the same thing. Now that is how we go from the original function to the derivative. So I'm going to kind of circle this in blue, and I'll circle the original function in red because the derivative comes from an original function. That's why it's called a derivative. Derivative means something that comes from something else. So the derivative function comes from the original function, the original position function. So now we're going to move downstairs and we're going to talk about the derivative of this velocity function, which we already know is acceleration. So if p prime of t is the first derivative, how do you think we go and calculate another derivative here? Well, what we can say is we can, in terms of the original position function, we can put 2 primes on it, and we can say that this is p double prime of t. That means, this notation means you start with the original derivative, then you take one derivative and get this thing, and then you take another derivative to get this one. That's, in words, what we were doing here with the pictures, right? And we've already said that this was equal to the acceleration as a function of time. We said that. So you could call it the acceleration, or you could call it the second derivative of position. Or you could call it the first derivative of the velocity, right? Because if you start with the velocity, which is this curve, and take one derivative, you could come downstairs here, right? And there's many different ways to write it, I guess is what I'm trying to say. Now this p double prime, you could write it like this. This is another way we write derivatives. The second derivative of the position, we put a square over the d, and then dt squared right there. And another way we could write it is p with 2 dots right on top, like this. All right, so I don't want you to get too wrapped up in this stuff. Like we're going to do so many problems that it's going to be so easy to understand. But all I really want you to know is that if you start with the position function, you can take a single derivative and arrive at the velocity function. We can call it v of t, but we can call it p prime of t. We can call it dp dt. We can call it p with a dot on top. That's the derivative. If we start with this, the velocity, and take another derivative, we arrive at what we call the acceleration. But that's the second derivative of the position, right? Which is the first derivative of the velocity coming one level down from here. And d squared p dt, this means we take 2 derivatives in the notation of the rise over run, dp dt. We take a second one, we get d squared p d. It's not really a square, it's just a notation telling you that you've taken a second derivative of this position function over time. The 2 goes next to the d, and then it goes next to the variable on the bottom. This is just the way it's written. Or you could put p double dot on top, much like we had a single dot up here. All right, as we talk about derivatives in the rest of this lesson and for the rest of your life, I want you to have a prototype example in your mind. And the prototype is always position, velocity, acceleration. You start at the top level with position, you take a single derivative and you get a new graph called the velocity, which governs the velocity of the particle. But if you take another derivative, starting from velocity, moving one level down, then you arrive at acceleration. And that is the derivative of velocity, or can be expressed as the second derivative of position. In your mind, I want you to think about that and just know that anytime you see the word derivative, replace it in your mind with rate of change. So this is motivation. This is getting you to understand conceptually what a derivative is. It's all about trying to see how things change. Because if I have simple problems in science or physics where things are moving very slowly or in a straight line, then everything's easy. But in a rocket, when you accelerate off the ground and you're just going faster and faster and faster, everything's changing all the time. Your velocity is changing, your acceleration's even changing, the drag on the spacecraft is changing, the pitch angle of everything is changing, everything's changing all the time. And so calculus is so important to know and to understand because in real life, everything is changing. You want to study the weather? Everything's changing. You want to study electricity and magnetism and waves? Everything's changing. If you want to study interference, if you want to study quantum mechanics, if you want to study anything in chemistry where the concentration of the chemical reactants are changing over time as the reaction goes to completion, everything's changing. So calculus is used everywhere because everything's always changing. So now we have to take a step further and not talk about the conceptual and start to talk about the definition of the derivative in a little more detail. But remember, it all comes back to the slope of a line, rise over run. Okay? If I were to give you a very simple graph, I'm just going to draw it really small because I don't want to clutter my main board space over here. And this could be it doesn't matter, it could be a function of x, it could be like some temperature as a function of x or something like that. And it's like some straight line, goes up, right? A straight line. What if I asked you, what is the rate of change of this function? Well, you're going to know it's a straight line. And so when I say, what is the rate of change? I'm not asking you, what is the value of the function here, here, here. I'm asking, how fast does the function change? What is its derivative? Well, if it's a straight line, then rise over run right here is the same value as rise over run here, which is the same value as rise over run here. The slope of this line for any line is always the same on the same line. So the rate of change for any line is just a number. It's just the slope. It's always the same, right? So it's very easy when things are linear is what I'm trying to say. So calculus, as I'm going to draw here in a second, is mostly used when things are changing all the time. And so let's talk about an example like that. Let me draw a more complicated graph, more complicated than the straight line that I drew right there. So I'm going to draw a crude little axis here. And instead of a function of time, I'm going to call it a function of x. In math class, usually you have a function of x. But just so you know, we could be talking about something as a function of time, like the electric field changing over time, or the temperature in a room changing over time, or the velocity of a particle changing over time. But x could be an actual distance variable. How much does the pressure change over some distance from here to here, right? How much does the force on a box change as the box moves from here to here? So this is in terms of x, but just know that you could change it to time, you could change it to space, you could change it to momentum in physics, you could change it to studying anything you're studying. All this stuff is applicable to everything. Let's put a function in that's more complicated than the line that I drew right here. If I had something I was studying that looked like this, what if it were to come up like this and then come down and then like taper out like this? This graph actually looks very similar to something you study in physics called black body radiation. When you heat things up, it tells you the frequencies of the light that will be emitted from it. When you put a poker, a piece of iron in a fire, and you heat it up and you pull it out and it's glowing orange, this graph, or a graph very similar to this, will govern the frequencies of the light coming out, emitted from the metal. It's called black body radiation. We study this kind of thing all the time in physics. But in this case, I'm just calling it generic f of x, but in physics it could be related to radiation, for instance, is what I'm trying to tell you. Okay? What if I draw on this graph, I put a point right here, and I come down here onto the x-axis, and I label this point A. And this is the x-axis. So this is a function, and so I can put the value of a into this function. I can calculate f of a. A is a number. When you see a could be 2 or 3 or 5 or whatever, but I'm just using a as a placeholder, right? What if I ask you, tell me the derivative of this graph at the point A? Well, what do? You say, well, the derivative means what's the rate of change. That means I have to draw a line tangent to the original graph, and I have to find the slope of that line. And that tangent line only touches the original graph at one tiny point. That's what a tangent line is. So right here, if I were to draw it, I could hold my meter stick up, but it may not be so great, but I guess I could try. So this is roughly the line tangent to this point. You see how it's barely touching the curve at one point, just kissing it right there. What is the slope of this line? Well, a horizontal line is 0. A line at 45 degrees has a slope of 1. When you do rise over run, the slope is going to be 1, right? And infinity is a slope like this, up and down. This is a line vertically has a slope of infinity. And anything just cocked a little bit off of vertical is just a very high slope. So it's going to get bigger and bigger and bigger, approaching infinity. So this is less than infinity, but it's a positive slope, much, much bigger than 0, right? How would you actually calculate mathematically the slope of the line tangent to the curve at A? How would you physically do it, right? Well, if you were doing it graphically, what you'd probably do is you would take a point far away first. You would get a very crude approximation. Let's do a crude approximation. I pick a point over here, which is very, very, very far away, okay? And this point, if I draw a dotted line down, I'm going to call this the X position, okay? This is A, this is X, right? And if I wanted to do like a very crude approximation for the slope of the line right here, then what I would do is I would just draw a line through these 2 points, which I'm going to have a hard time getting perfect, but that's roughly it. And I would calculate the slope of this line. And I would get it's very close to 45 degrees, so I would probably get a slope very close to 1. And I would say, well, that's a pretty decent approximation because we know it's higher than that, but we are getting pretty close, right? How would I get a better approximation? Well, what I would do is I would just take this point and I'd move it closer. And I would draw a line through those 2 points, and that would be a higher slope. Okay, well, how would I get a better approximation? I would draw a point closer, and then I would draw a line through these 2 points. And I would make it closer and closer and closer, and eventually I would get a microscope out, literally a microscope, and I would zoom in on this point and I would see the purple curve, how it's changing, and I would take a point so close to that original point that I might as well just say it's just an infinitesimal distance away from the pink dot that I care about, and I would call it, I would put a d in front of it to call it like df, because this is a function f instead of a function p. I would call it df. And because it's so close in time, or space, or whatever it is I'm talking about, I would call it dx on the bottom, or dt, whatever variable I'm studying. The d would just simply mean teeny tiny, extremely infinitesimally close, and then I would calculate the slope between that teeny tiny point far, very, very close to the line in question, and I would call that the derivative of this original purple curve at the point A. But notice that every time I told you how do we calculate the derivative, I told you we start far away and find the slope of this line. Then we get closer, find the slope of this line, closer, find the slope of that line. Every time you're doing it, you're finding the slope. The slope is rise over run, just like it is from algebra, right? So how would I find the slope of this line right here? Well, this line has a run between these 2 points. I'm going to call this the run dimension, like this, because that's how far over I go this way, between this point and this point. And then it has a rise, which is like something like this, which is the vertical distance between these 2 points. So this is the rise. You see, that's how we find the slope of any line between 2 points. It's the rise divided by the run. That's all I'm trying to do. So what I would say is that would be the rise over run. And what I would say is well, what is the rise anyway? What is the rise? Well, if this is the point x and this is the point a, if I want to figure out the values of the function here, this right here is f of a. So, and this is f of x. So right here, this is f of a. And right here, this is f of x. I just take this value, stick it in the function, and then out comes the output. Stick this value in the function, out comes the output. So if I want to find the rise, I just have to calculate this and subtract this away. So what I would really do is I would take f and evaluate it at x, which is this value, and then I would subtract this one right here, f of a, and this value would be the rise. That would be how far this line travels in the up direction. But then to calculate the slope, I have to divide it by the horizontal run, which is the distance x minus a. So x minus a would be on the bottom. You see this kind of thing in calculus books, and it flips people out because it looks so complicated. But it's literally nothing different than slope of a line from algebra. Rise over run. It's just that these points don't have numbers, they have letters. But that's all you're doing. The difference on the top is how far this line goes up. And the up direction is going to be f of x minus f of a. That's going to give me the two outputs of the function, subtract them, and then the horizontal is just the subtraction here. But this is the slope of the line I have drawn here, right? But how do I handle the situation of making it closer and closer and closer and closer and closer? Well, here is where I take the limit. I take the limit of this whole thing, and I let the variable x approach the value of a. That is the magic. This thing, the limit, that's the magic. That's why we spent so much time studying limits. When you get into calculus, you study limits and limit this and limit that, and it approaches it, it never gets there, and you're like, why am I learning this? This is why you learn it, because the definition of the derivative is all in terms of limits, right? So if I allow x, this value, to approach a, that means I grab x and I move it closer, which means this point gets closer and closer and closer and closer, and this line gets closer and closer and closer to the true tangent line, which is about right there. As this thing approaches the value of a, remember a is a number, so x could approach, if a is 1 on the axis, then x would be approaching 1. And this thing, as it gets closer and infinitesimally close, I'm calculating the slope of the line that results as I get closer and closer and closer and closer. And I call this entire calculation the derivative of the original function evaluated at the point A. So this is the definition of the famous derivative in calculus. Notice that if I just throw this at you, it looks so complex, but really all it is it's telling you that you take the slope of the line between any 2 points on the graph, you make the 2 points get closer and closer and closer together to get to where it's a tangent line to the curve, only touching at one point, and you just relabel this whole thing and you call it the derivative of the original function at the point A. This is the slope of the line tangent to the curve at A. That's why A is here. You're taking the derivative and you're evaluating it at the point A, which means this point right here. Okay? This is absolutely critical. If there's any question in your mind what I'm doing, if you're a little fuzzy, just rewind and watch it 5 more times, okay? I can keep repeating myself over and over again, but I'm not going to say anything any more profound. It is simply the calculation of the slope of a line between 2 points, but then you make the points close together so that in the limit, you're taking the slope and finding the slope of the line tangent, which means infinitesimally, 2 points infinitesimally close together at that point, which means it's the line tangent there. And you relabel that whole thing and you call it the derivative at that point. Okay, now this is how we're going to, in the beginning, begin to calculate derivatives. We're going to calculate the slope of the line tangent to a curve. We're going to use this, and then we're going to learn a whole lot of mechanisms that are easier than this to calculate derivatives. But before we can get there, I need to show you that often you'll see this in a textbook, but you will often see it cast in a slightly different way. So I'm going to show you that next. Okay, what I'm going to do is I'm going to draw the derivative. Basically, it's essentially the same thing as this, but the equation for the derivative is slightly rewritten, which is a little easier to use for some problems, okay? So what we're going to do is draw another graph, right? So let me just draw another sketch, and just for variety, I'm going to draw it a little different, even though it's basically the same exact thing. So I'm going to call this x, and I'm going to call this f of x, okay? And the graph I'm going to draw, I guess I'll use the same color, purple. I will, do some wiggly wobbly thing that goes up, something like this. Some crazy looking graph. Doesn't matter what it looks like, okay? Now let's say I want to find the derivative of this graph at a certain point. And the point that I want to use, or to calculate the derivative at, is, let's call it right here. So I'm going to go down here, and I'm going to call this A. Notice I labeled it A, just like I labeled it A over here. All right, but instead of putting x right here, what I'm going to do is I'm going to recast it, and I'm going to say, well, how do I find the derivative of this point right here? Well, you're going to do the same thing. You're going to pick some other point relatively far away. You're going to draw a line through these points. You're going to find the slope. And then you're going to let this point get closer and closer and closer and closer, where eventually what you've arrived at is the slope of the line tangent, because the 2 points are so close together. But instead of labeling that point x, we're going to label this point h. You're going to find out that I'm going to write a slightly different version of the derivative limit on the board, but in the end, it's going to be exactly equivalent to what I wrote here. You will see both of them, so I just want to show you both on the board. But it's the same thing as we already learned right here. All right? Now, if I want to find the derivative of this point, I got to find the slope between these 2 points here. So between here and here, as before, we have the run direction. And remember, what we're trying to basically say is as an approximation, we're going to draw a line through those 2 points and find the slope of this line. Then we're going to let the second point get closer and closer to the first, eventually converging on a derivative like this. And this direction, from here down to about here, is the rise direction. So I'm going to call this the rise direction. So we're going to find rise over run just like we do before. To continue, I'm going to relabel this. Instead of calling it h, I'm actually going to call it a plus h. And so that this direction here, this is h units long. If this is like, if a is 4 and the width here is like 5, then 4 plus 5 is 9, a plus h is just down here. You start at a and you go h units over, that's the second point on the graph right here. Ultimately, this graph serves exactly the same purpose as the other one. So if I wanted to find the slope of this line here, I would have to do rise over run. So what would be the rise? Well, I would evaluate the function at a plus h right here. So I would say f evaluated at a plus h. But then I would have to subtract, that would be this value here, and then I would have to subtract the output value at this part, which would be f of a. So subtracting these is the rise, right? Because the output of the function is going to give you the output here and the output here, and you subtract them, it's going to give you the rise. But then I have to divide by the run, right? But what is the run? It's this minus this, right? But if you take this minus this, a plus h minus a, the a's go away, and the width here, as I already wrote down, is just h on the bottom, like this. This line is bothering me, so I'm going to try to make it a little straighter. Right? So this is rise over run. This is the subtraction of the outputs, giving me the rise. H, as defined by my drawing here, is the run. And so now all I have to do is I need to take the limit. And what do you think you need to do? If h is the distance between these 2 points, you shrink h and allow it to approach 0. And we call this the first derivative of the function evaluated at a. And this is exactly the second way in which you'll often see the derivative defined in terms of a limit. But I want you to not get flipped out because it looks like they're so different. They're not different at all, okay? Notice what's going on right here. In fact, if you start from this, I could have started from this. If I just said, hey, we're going to go from this, let's say that you define h to be the distance between these 2 points. Notice it's a and x. So what if I let the width h to be x minus a? Because x minus a would be the width, which I would call h, right? So I could put h right in here if I wanted to. And if I do that, I can solve for x, and then x would be h plus a, or a plus h. If I just move a to the other side, then I can sort of do this substitution. If I put it in here, what do I get? Well, for x, I'm going to stick this in here. Look at there. That's what I've got. For a, I'm not going to make any change at all, so a is going to stay right here. X minus a on the bottom is this. I'm going to replace it with h, so I'll replace the bottom with h. That's what I have right here. And the limit as x approaches a, but if you look at this first little equation right here, if you let x approach a, then you're going to get 0 and h is going to approach 0. In other words, as x gets very, very close to a, it'll be like a minus a, which will be 0, h will approach 0, which is how I have the limit written. So not only are these things, cousins of each other, they're really the same thing. Usually you're given both because depending on the exact problem you're solving, sometimes it's a little easier to write it down one way or another. Some books present only one and not the other definition. I don't want you to flip out about it. Basically, they're the same exact thing. All you're doing is you're taking the slope of the line going through 2 points as the rise over the run. And if you take the 2 points to be far away, then you have to somehow get them close together. In this formulation where you have a and then a plus h being the width here, you let the width h go to 0, bringing the points closer together. Rise is this, h is the definition of the run, because you subtract this, you get h here. And so shrinking h get to 0, it pulls off the limit and you get the derivative. The exact same thing is happening over here where we have defined a and x and we let x approach a. I think this one's easier to understand personally, but they're the exact same thing. Okay? So now before we do our problems, I want to talk a little bit about what we've learned before we jump into our actual problems. A lot of people want to kind of like just get to the problems, which is great. I understand that. But this is kind of like you need to let it bake in the oven a little bit sometimes. So we need to talk a little bit more about rate of change. So when I say something like, when I say instantaneous rate of change, right, I might say something like f prime at A is the instantaneous, that's what INST means, instantaneous rate of change, triangle means change, rate of change, of f of x with respect to, that's what WRT means, with respect to x when x is equal to A. So this is the kind of thing you'll see in a book, but it'll be written in a box with a theorem and it'll be like very scary looking. All this thing is saying is that the derivative f prime evaluated at A, when x is A, is the instantaneous rate of change, which means it's the slope of the line tangent to the curve, which is what I've been saying, of the original function with respect to x, because that's the variable we're studying, when x is equal to A. So you see these kinds of words in books, but I'm trying to break it down and make it not so scary, because these words just simply mean what I've been saying over and over again, that to find the derivative right here at this point, it's the instantaneous rate of change of the original function with respect to whatever variable you are studying, which is the slope of the line tangent to the curve, which is what we were saying here in the beginning. The slope here is different than the slope here, is different to the slope here. And the units go from meters to meters per second. That's the rate of change with this thing as a function of time. And when you take a look at how the velocity changes over time, you get a new unit. And so it's all, in order to take a derivative, you have to study something with respect to something else. Usually it's time or space. So I want to give you a couple of more concrete examples about that before we jump off. When we say rate of change, when I say rate of change, I've been using this for the derivative, but actually it's very, very instructive to go back to something I just briefly touched on, df with respect to x. This kind of notation, when I first learned calculus a long time ago, I kind of blew over that. I didn't care about it. I did f prime of whatever it was because it's easier to write down. And that's fine. That's okay. But don't overlook this, because this kind of notation is what comes back over and over in physics and engineering and chemistry and math. When you get beyond the basic calculus, you start using this a little bit more, because when you're deriving things in physical sciences, you're interested in tiny, tiny changes in the function f over tiny, tiny distances, dx or dt if it's time that you're studying. So when you see the d, the little d, df or dt or dx or dy or dz or whatever it is you're studying, in your mind, as I've said before, you replace it with an infinitesimally tiny, tiny, tiny change in the variable f with respect to a tiny, tiny change in with respect to x. So if I say f prime of a is the instantaneous rate of change of the function with respect to x when x equals a, what I'm saying is I'm taking the derivative of the function with respect to x and I'm evaluating it when x is equal to a. I'm taking the slope of the line tangent and I'm evaluating what that slope is at the point of interest, okay? Right, so just to bring it home, we'll draw two little graphs and I'll try to explain what I'm talking about. I've already talked about position, but I'm going to revisit it one more time. What if I have the position of a particle that looks something like this as some function of time? This is a position p, so I'll call it position p. Position p is a function of time. In other words, it's getting farther and farther away, and then it comes a little closer to the origin, then it gets farther away, and it comes back closer to the origin, and so on as time goes on. If I want to know the rate of change of the position as a function of time, at this point, then it's going to be the slope of the line tangent to the curve right there. That's going to be it, right? If I want to know what the rate of change of this function is with respect to time here, at this point, it's going to be the slope of the line tangent here, which is like a flat line. So the slope of the line is less right here, right? And over here, if I were to continue the graph downward, something like this, and I wanted to figure out what is the slope of the line tangent right here, well, notice that the tangent is actually going the opposite direction. So this is a positive slope, and this is a negative slope. And so a positive slope means it's changing in the positive sense, maybe like it's speeding up, and the negative slope is changing in the negative sense like it's slowing down. But it's always the slope of the line tangent to the original curve, right? And so as we've mentioned before, but it's so important, I'm going to say it again, that the position, the derivative of the position with respect to time is dp, the derivative of the position with respect to time. This is the slope, which is where you take a tiny change in position divided by a tiny change in time. And the answer you get here is in meters per second, because once you start comparing distance and time, you have to have a unit compatible with that. But let me give you an example that doesn't involve distance and time and velocity, just to kind of bring it home before we close this little section out. What if I have a bar? So I'm going to draw the bar like a physical bar of metal or something like that under here. You could think of this like meter stick being like a bar or something. And underneath this bar, I put some kind of candle flame like this, something like that, very, very hot, right? Then what if this was the temperature, you know, and you could call it T, and this is going to be a function of not of time, but of X, of position. Because if this is like a meter stick, then what you could say is like this is the origin, and this is like 10 centimeters, 20, 30, 40 centimeters away. And so over here it could be like 50 centimeters away. This is a function of position along a bar. What would the temperature curve look like along this bar? Well, right near the flame in the center, the temperature is going to be very, very high. But very far away, the temperature is going to be low. It may not be zero, but it's going to be lower. So put something like that. And far away over here, it's going to be also lower. So I'm just making this up, but it might look something like this. The temperature might reach a maximum right there, and it might go down like this. Now, my graph is lumpy, but you get the point. So if you were studying something like this, where it was temperature as a function of distance, which means meters, temperature as a function of meters, and you had a flame in the center and this was hot and these were cold, what if I asked you, what is the derivative of this curve at this point right here? Well, then what you would do is you would draw a line tangent to the graph and you would say, what is its slope? And then what if I said, what is the derivative over here? You would draw at the very, very top, you would draw the line tangent to this point right here, and that would be the derivative. And what if I said, what is the graph over here, or what is the derivative over here at this point? You would draw a line tangent over here. This derivative will be positive because the slope is positive. This derivative will be negative because the slope of the line tangent is negative. This derivative will be zero because it's exactly flat right here, right? And what you would then say in terms of math is you would be taking the derivative and calling it t prime of x, the derivative of the temperature as a function of the distance. And you would say that that could be equivalently written as dt, the change in the temperature, divided by or compared with the change in the x direction. Notice it's always comparing two things. The change in the temperature compared with the change in the distance or the dimension of position along the bar, right? And what would be the units of any of these derivatives? Well, if the units of this were in degrees Celsius, right, and the units of this were in meters along the bar, then the units of the derivative would be degrees Celsius per meter. Just like it was meters per second, here the units of the derivative, the rate of change at any point along that bar, would be degrees Celsius per meter. So what would it be telling you? It would be telling you that right here over here, the derivative is the highest. The highest of any of the purple lines I've drawn in this figure. And it's also a positive number. So that means that the temperature as compared to the x direction on the bar is increasing the most rapidly right here. And over here, the temperature is decreasing because it's negative. The degrees Celsius per meter would be a bigger number negative here because it's cooling off very fast right here compared to the distance. But what would the derivative be in the middle? Well, we're very, very hot in the middle, but we're also very, very hot to the left and very, very hot to the right. We're also really, really hot over here and really, really hot over here. The temperature is just not changing as fast in the center because it's all very hot. So the derivative would be zero. The degrees Celsius per meter, it wouldn't be changing very fast per meter. In the middle is what I'm trying to say. So it's useful to think of different examples of what a derivative is, because in real life, there's lots of examples. In electromagnetism, it's volts per meter for the electric field. You also have units for the magnetic field. How fast is the magnetic field changing per time or changing per distance away from your antenna or whatever? Okay. Here, the derivative is a big number because the temperature is changing compared to the the travel distance along the bar very, very fast. The slope of this line is thus bigger. But over here, the temperature is pretty constantly high, so at the very, very center, the derivative is exactly 0. It doesn't mean the temperature is 0, okay? It just means the temperature is not changing at all at the very, very top. But then if as soon as you get off to the top, then it's either positive or negative there. And then you have a very high negative derivative showing you that you're cooling off very fast. So very, very high heating up compared to x, very, very high cooling off compared to x, and in the middle is not changing very much at all. All right, so what I need to do is erase one of these boards and we'll solve one quick little problem to wrap our brains around derivatives with real numbers. All right, here's our first actual problem. We have a piecewise defined position function, x, as a function of time. And so what I want to do is figure out what the velocity curve will look like for this thing and try to write that down and also to sketch the velocity curve. All right, now in all of our previous examples, and we will do more complicated examples looking like that very soon, we had very smooth curves. And so the derivative was the slope of the line tangent. But in this case, our position curve is a straight line, a straight line, a straight line, a straight line, and a straight line. So what you do is you break up each little segment and treat it as a line, and to find the derivative of this curve, you have to look at each little segment and find the slope of each of these lines. And then you reconstruct that as the velocity curve, and that would be called the derivative. But in this case, it's piecewise defined because it has these kinks in it. In general, in nature, things don't have kinks in their graphs. Usually things are smoothly changing, but this is a good example to learn nonetheless. Right? So what we do is we break this thing up. First, we're going to go into the first little window here from 0 to 1 second. This is 0 to 1 second. So what we do is we say 0 to 1 second, right? And we want to find the slope of this thing. What is the slope? Well, the slope is going to be rise over run. Well, it goes up 3 units and it goes over 1 unit. So if you want to be rigorous about it, what you say is it goes up 3. The y value is 3 and then minus 0, which is the original value. So 3 minus 0 and then 1 minus 0. So rise over run. So how far up does it go? 3 minus 0. How far over does it go? 1 minus 0. And so what you'll get then is 3 over 1 is going to be 3. And so the slope is 3. So what we'll do is calculate all of these and then we'll reconstruct it into a graph in just a second. Now the next window is going to be this window right over here from 1 to 2 seconds. So I'll call it 1 to 2 seconds. And so here the slope is, well, this is a flat line. So if you want to be, the slope of a flat line is 0, but to be rigorous about it, you would say, well, the y value is 3 here and 3 here. So 3 minus 3, that's y2 minus y1. And then the time value is just 2 minus 1. So rise is 3 minus 3, run is that, and so you're going to get m is equal to 0 for that window right there. Okay, let's go back here, and from 2 to 3 seconds, right, we're going to be in this window right here, from 2 to 3 seconds, the slope is going to be the second y value. The second y value is 1, and then the initial y value is 3. So it's actually going to be y2 minus y1, and then you're going to go 3 minus 2. So the second point minus the first point. So 1 minus 3, 3 minus 2. It's just rise over run just from basic algebra. And so what you get here is negative 2 on the top and positive 1 on the bottom, so you get negative 2 for the slope. So notice we have a positive slope here because the slope of this segment was positive. We get a negative slope here because the slope of this line was negative. And we get a slope of 0 in the middle because we have a flat line slope right there. Now, in between 3 and 4 seconds, we have 3 to 4 seconds. I'm not even going to calculate this. It's another flat line. I'm just going to put slope of 0. You could subtract the y values, 1 minus 1, and then 4 minus 3, and you're going to get a slope of 0. And let's go ahead and try to squeeze in the last one over here. But notice that this is a single straight line, so we can go and use this 2-second window from 4 to 6 seconds for our last window here. Y2 this is supposed to be 3, and then here is 1, so 3 minus 1 for the y values. So it's going to be 3 minus 1, and for the time value, 6 minus 4. And so what you're going to get for the slope right here, 2 divided by 2, you're going to get a slope of 1. All right? And by the way, the units of this, if this was in meters and for the position and seconds for time, then all of these slopes, which would be the velocity curve, would be meters per second, the velocity. All right, so if we wanted to write this thing down in a rigorous, kind of like a mathematical way, you could say x prime of t, which is the derivative, but we could also just call this the velocity as a function of time, because we know that that's what the derivative of the position is, right? And because it's piecewise defined, we would have to kind of like write it in a piecewise way. For the first little bit of it, we would say that the velocity was equal to 3 meters per second, but that is only in the range of 0 to 1 second, so it'd be 0 less than t less than 1. And then we would have 0, but that would be in the window of 1 to 2 seconds, so 1 to t to 2. So this is t bigger than 1 second, t less than 2 seconds. Right? And then we would have a slope of negative 2 meters per second, and it would be from 2 to 3 seconds, so 2 less than t less than 3. And then we have a slope of 0, which would be the 3 to 4 seconds. T is bigger than 3, less than 4. And then we have a slope of 1. And that one would be from 4 to 6. So 4 less than t less than 6. So this is the way you would write it down. And if I were to ask you, which of these situations is the particle moving to the right? Which of these situations is the particle moving to the left? Which of these situations, or what regions of time, is the particle stationary and not moving at all? Then what you would do is you could say, well, obviously when the derivative is 0, the velocity is 0, and the particle in these time windows is not moving at all. And so you would say the particle is still here. And you can see that the particle is indeed still here, and so that makes sense. And here it's moving to the right at 3 meters per second. Here is also moving to the right at 1 meter per second. So these are both positive. Positive derivatives mean moving toward positive x. And so they're moving to the right. And then this one's negative, which means the particle was moving backwards to the left. So in terms of one-dimensional motion, you can see from the graph, it is moving away from the origin here, then it's motionless, but then it comes back toward the origin. This means it has to move back to the left towards the origin here, but then it's stationary again, then it begins moving away from the origin again. The derivatives, meaning the velocity of the particle, also can tell you which direction the thing is moving, okay, in addition to the position graph. Now, if you wanted to draw this or sketch it on a graph, then we could certainly do that. We could draw a little graph right here. We could say this is time. We could say this is velocity as a function of time, which, don't forget, is the first derivative of position, right? And if you wanted to write it in terms of dp, dt, you could write it like this. So all three of these things mean the same thing. P prime of t, dp dt, velocity as a function of time. Same exact thing. And then what we could do is we could go out to 6 seconds. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 seconds. And then we could go up to 1, 2, 3, and then negative 1, negative 2. So this is 3, and this is negative 2. And then what we could do is we could say, okay, between 0 and 1 seconds, our speed, or our velocity, or our first derivative is 3, right? So we would have, between 0 and 1 second, we would have a graph that was something like this. And then between 1 and 2 seconds, the derivative was 0, so I'm going to erase my little axis here. And between 1 and 2 seconds, I'm going to put a blue bar down there, meaning the velocity is 0 right there. And then between 2 and 3 seconds, it was negative 2. Between here and here was negative 2 down there. And then between 3 and 4 seconds, again, the velocity was 0 between 3 and 4 seconds. So like that. And which means it down at 0 again. And between 4 and 6 seconds, it was 1 meters per second. And so this is 1 meter per second. So between 4 and 6, something like that right there. Okay? So this would be the graph of the velocity. High velocity, no velocity, a negative velocity, which means moving back to the origin, motionless again, no velocity, and then moving to the right again, but not as fast as it was before. So this is a long lesson. The first lesson in something as critical as a derivative is got to be a little longer. I could split the lesson up, but then you're not going to have it all in one place, and making the connection between different concepts is difficult if everything is spread out. Now, the future lessons will not be nearly as long because all of this groundwork is laid. Before we leave, though, we're going to do a speed run through the whole thing because it's critical to let it bake in the oven a little bit. The prototype you should have for a derivative is the rate of change of a function. The prototype is position, velocity, acceleration, because you have experience with that every day. Position curve is how far away something is from the origin as a function of time. When you want to know what its velocity is, you take what we call the derivative, which is its rate of change. How fast is the function changing over some period of time? And the velocity is changing as the curve goes on because the slope of the line tangent to this curve is always changing. So the slope is low here because it's very, very close to flat, and the slope is high here, which means the derivative is high. Notice the derivative I gave you, which we will learn how to calculate later, is a line with a slope of 2. And so, of course, it should be steeper than this, but you get the idea. It's a line here. When you take the derivative of this, you get what's called the acceleration curve. Right? Notice that the units go from meters to meters per second, which is meters per second squared. In terms of notation, we start with a position. We call it p prime of t to get the first derivative, and we call it p double prime of t to get to the acceleration. We can also call that the first derivative being the velocity, and then the second derivative, we can call it the acceleration. Now, instead of calling it p prime of t, we have other notations. We can call it dp dt, which is rise over run. How much does the function change with respect to time? And we could also put a dot over there to represent the derivative as well. Now for that second derivative, we have to write it like this with the squares here, and we'll do more of that later, but this is just indicating we've taken 2 derivatives, and then 2 dots means we've taken 2 derivatives. Now, spoiler alert, you can take a third derivative and a fourth derivative and a fifth derivative if you need to for your problem, but in general, going past the second derivative is not typically needed for most problems in physics and engineering. I mean, usually. Of course, there are always exceptions, but usually you just don't need to because the problem isn't necessary to solve with higher derivatives, okay? Now, this is conceptually what it is. It's the slope of the line tangent to the curve, right? Then to calculate it, we have to roll up our sleeves and calculate it, and we do it with limits. To find the slope of the line tangent to this curve, we just pick a point far away, we draw a line through them, and we find the slope of this line. The slope of this line is the rise divided by the run. The rise is the output of the function here minus the output of the function here. The run is x minus a, which is the distance along this axis here. But then we tell the 2 points to get closer together, allowing this tangent line to become touching only at one point when x approaches a. When we evaluate this limit, we arrive at what we call the first derivative at the point a. Now, we can recast this exact same thing into a slightly different form that you will see in many books. And I want you to know that it's no different than what we have already learned. And I absolutely hate this F. So even though the lesson's over, I'm going to put an F right there. All right. And it's the same thing, though. You have a graph. You have 2 points. You're allowing them to get closer together, but you label this one A, this point A, and you allow this to be A plus some width along the x direction, A units that way. And it's the same thing. To find the slope of this line, it's the rise over run. So it's the output of the function here minus this one. So the output of this point along the x-axis would be this, minus the output at f of a. That's the rise. And the run is how far separated they are, which is h units here, right here. So it's exactly the same thing. And you allow h to go to 0, bringing the points closer together. We said you could get this recasting of it by starting with what we had and basically doing the substitution. Let a equal x minus a, and so if x approaches a, then these two things are going to approach 0, and so it'll be the same thing as h approaching 0, giving me this. And then here with x, we just replace it with a plus h right there, and then in the bottom we replace it with h. So just doing a transformation, we get to this, which is a very common way to see it in a textbook. So you can use either one. I mean, I just want you to know that it's no real different. It's calculating rise over run. And then we just did our problem. So this is an introduction to derivatives. We have a long road ahead of us, but I promise you that if you understand the slope of a line, you can understand the derivative. And it really unlocks the whole universe to study. In real life, things are changing, all the time according to different curves that are not linear. Lines are what we study in algebra because they're easy to understand, and we learn about the slope of a line for so long in algebra, partly because it's not because we care about the slope so much, it's because the derivative comes from it. And the derivative is basically what calculus is built upon. Like the whole entire subject of calculus is built on the derivative. So go through this again. I recommend you watch it a couple times. Follow me on to the next lesson and the several lessons beyond, where we will really get a good intuitive feel for these definitions by applying them. And then we'll learn how to take derivatives until it's so easy for you that you'll just be able to do them in your sleep. So watch this again. Follow me on to the next lesson. We'll continue to build your skills. Learn anything at mathandscience.com.